Okay, so welcome back. Yesterday I stopped with a discussion of phase portraits for autonomous systems, or for autonomous. We'll get there eventually. Um, for our autonomous equations. So an autonomous first order equation looks like this. This process that we're going to do for these does not work for a general separable equation or any other kind of equation. Only works for autonomous equations like this. So there's no if there's a t showing up on the right hand side when you write it like this, then this whole analysis doesn't really work. So I wanted to generate phase portraits. Uh, so let's do a quick example. Um, so I'll just make up something off the top of my head here. So let's consider the following. Let's do something like y times y plus 1 times y minus 2. And let's do y, say, minus 3 squared. Okay. All right. So there are a couple of steps in this process. So first of all, what is it that I'm being asked to do here? So let me give you what it is I'm wanting to do here. So determine, uh, so maybe the following, right? So answer the following. So a couple things, and this is pretty representative in general of what we're trying to do in these problems. So a couple of things. So one, identify the stationary solutions for this equation. So that's the first thing I want to do, right? Stationary solutions we found are exactly where this right-hand side function is equal to 0. So that's equivalent to just finding the zeros of g of y. Now, this g of y need not be a polynomial. It could be a trig thing. It could be a more complicated thing. The point is that we're finding zeros of it regardless. So whether it's a polynomial or not, frequently it will be a polynomial given to you in some form like this so that you can nicely determine those things. So second is sketch some potential solutions and indicate their long-term behavior. Okay. Included in is kind of like a sub question here, but I'm going to write it as a question 3 here. Um, so maybe, like I said, question 3 here, I'll say answer questions about long-term behavior of the form. Here's a few. If, right, so let's say that we have some initial condition here. If y of, we'll take t sub I to be 0 here. Or no, actually not. Well, let's do this. So if y of t sub I is equal to 1, what is the limit as t goes to infinity of y sub t? What is the limit as t goes to minus infinity of y sub t of y of t? If y of t sub I is equal to, say, minus 1, what are both of these limits? Okay, these are the sorts of questions that I want to be able to answer from this process. And then lastly, I know that this numbering is kind of weird, but I think it's nice to put this all on the same sheet. Classify the stability of each stationary solution or stationary point. We'll see what that means when I get around to it. Okay. This is also going to have implications for some of the terminology that we do near the very end of the course. Okay, so we'll be returning to this much later near the end. But anyway, for now, these are kind of the main things we want to address for a problem like this. Okay. So how do we answer these problems? I'm going to copy this on the next page. So the problem in question is dy dt is equal to y times y plus 1 times y minus 2 times y minus 3 squared. So the first question is identify the stationary solutions. The stationary solutions are where g of y is equal to 0. Now, of course, this whole thing is g of y, right? And our viewing this as an autonomous equation in this form. Okay, so this is g of y. So stationary solutions are where g of y is equal to 0. In this case, this is a factored polynomial, so saying g of y is equal to 0 here means I'm setting this polynomial thing equal to 0. It's already factored, so it's a product of a bunch of things where this thing is equal to 0 is, clearly indicated by the factors here. So what are the stationary solutions? So stationary solutions for this particular equation are y equals 0, y equals minus 1, y equals 2, that's from this factor, and y equals 3. Okay, so here are my stationary solutions. Now, at the end of lecture yesterday, I indicated how we go about the rest of this process. So I draw a copy of the y-axis. Now, you might be confused at first because, this is in the ty plane, right? This is the y-axis, this is the vertical axis, but I'm drawing it horizontal here. Okay, we're going to draw another version of this picture. So sometimes this is called the face portrait, and sometimes the sketch that results from this info is called the face portrait. It doesn't matter. The thing is that when I'm asked to sketch a solution, then I'm drawing a plot in the plane. Otherwise, I care about what goes on this. The point is that these values divide the y values into pieces. So I can just mark these things. So here's minus 1, say. Here's 0. Here's 2. And here's 3. And so these points, these stationary points, or these stationary solutions, divide up the y values into pieces, right? There's the piece that's to the left of minus 1, so everything less than minus 1. Between minus 1 and 0, between 0 and 2, between 2 and 3, and to the right of 3, or greater than 3. Okay, so at each of these points, the value of the right-hand side is 0. Because g of y is going to be assumed to be continuous, right, so that we, by existence and uniqueness, we have all the nice stuff resulting from that. Because it's continuous, since these are the points where it's 0, in between these points, g is either positive or negative. Well, I want to test the sign, right, of g in between each of these points. So I look at this thing, and I say, okay, to the left of minus 1, what's the sign of this? So to the left of minus 1, so you're thinking of values like minus 2, minus 3. You're also thinking about values like minus 50 million, right? So to the left of minus 1, what is the sign of g? So this y term is negative. This y plus 1 term is also negative. The y minus 2 term is negative. The y minus 3 squared term is positive because you're squaring it, so that thing is always positive. In fact, for sign concerns, right, this thing is always positive. So I would have a minus times a minus times a minus times a positive. So the resulting sign is negative. And so I'd put a minus here, and I would draw arrows moving to the left. We'll talk about what the arrows are implying here in a second. Okay. In between minus 1 and 0, I do the same thing, the same kind of sign analysis. So I say, okay, between minus 1 and 0, what's the sign of y? Well, it's negative, right? Between minus 1 and 0, what's the sign of y plus 1? Well, that's positive now, right? You're thinking of values like minus 1/2, for instance. Minus 1/2 plus 1 is positive, so I would have minus times a positive times y minus 2, that's going to be negative. So negative times positive times negative times positive. This is always positive, right? So negative times positive times negative times positive. So this is positive. I put a plus there, and I draw arrows moving to the right. Okay. So I repeat this process for every single piece. Okay, so the more pieces, the more times I have to do it. Between 0 and 2 here, what's the sign of this thing? So between 0 and 2, now y is positive. Y plus 1 is positive. Y minus 2 is negative. Y minus 3 squared is positive. So positive, positive, negative, positive. So this is a minus. And again, I draw arrows going to the left. Remember yesterday I told you that this may cause flashbacks to Calc 1 when you did this kind of sign analysis on intervals for the first derivative test, right? This is how you showed that a thing was increasing or decreasing on the intervals indicated. But that's exactly what you're doing here, right? In a sense, this is a first derivative test because this right-hand side function, whether this is positive or negative, is telling you whether the first derivative of y, dy dt, is positive or negative. So essentially what you're doing is a first derivative test. Okay, so between 2 and 3, what are the signs here? So between 2 and 3, this is positive, this is positive, this is now positive, and this has been positive in every case. So my arrows go to the right. Oh, that's positive. To the right of 3, positive, 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 positive again. So again, I get a positive thing, and the arrows continue going to the right. Okay. All right, so now it is time. We've finished our picture. Okay, we finished our face portrait. Now it's time to interpret what this means. Okay, so these arrows indicate the behavior of the solutions as t increases or goes towards positive infinity. Okay, so as t goes towards positive infinity, it follows the solution, the values of y, follow the arrows. Now, why does this work like this? Well, we saw yesterday that due to existence and uniqueness, right, if I draw a portrait here, so here's 0, so here's y equals 0. So this is now in the ty plane, so this is, this is of course the t-axis here, but I don't have to have the 0 as a stationary point. Here is 2. Y equals 2 is here. Here's y equals 3. Here's y equals minus 1. All right, so there's my 4 solutions that are stationary, right? Meaning that if I were to plot these solutions, they're just horizontal lines at these heights. So what's the behavior of these solutions as t goes to infinity, they just remain constant, right? So because of existence and uniqueness, any other solutions having, say, different initial values, right? So I have y of t sub I is equal to some initial value y sub I. So if my initial value is -1, then the limit as t goes to infinity of y of t is just -1. It just stays along this line. But if I have some initial value, say like here, between 0 and 2, so let's say that y of t sub I is equal to 1. Okay, this was a question I asked here, right? So here's a question I asked. If y of t sub I is equal to 1, what's the limit as t goes to infinity of y of t? What's the limit as t goes to minus infinity of y of t? So what I know already before I've thought about anything is that due to existence and uniqueness, whatever the solution does, it can't go out of bounds here. It can't cross the line y equals 2. It can't cross the line y equals 0. Okay, for reasons that I mentioned last lecture. So it's at least bounded by these things. But how's it actually working here? Well, between 0 and 2, the arrows are moving to the left. These arrows indicate a motion toward 0. Another way of thinking about this is because the sign here is minus everywhere on this interval between 2 and 0, this sign is minus. Well, that sign is the sign of dy dt. So if I'm plotting potential solutions, y of t, right, what I'm saying is that if its initial value is 1, that means between 0 and 2, the sign of dy dt is negative, means it's decreasing. And so what a potential solution might look like would be this. Okay, we know it can't cross or touch this thing, so it's decreasing towards 0. If my initial value was something like that, right? Maybe it was like 1.5 instead, then maybe it does something like this. If my initial value was, say, here, maybe it does something like this. Again, these things are not allowed to touch or cross, so I'm being very careful here. Okay. What is this saying? It's saying that the limit as t goes to infinity of y of t, if the initial value of y is 1, is 0. Okay. What about, that's not the only type of limit I asked. I also asked, what's the limit as t goes to minus infinity of y of t? So to see the behavior indicated by this picture here, when you're going towards minus infinity, you're going in the opposite direction to the arrows. So your initial value is between 0 and 2, so I'm looking at this piece. As t goes to minus infinity, I'm going in the opposite direction of the arrow, so instead of going towards 0, I'm going towards 2. You can see that in the picture. This picture is me, stopping at my initial time t. I could extend this picture if you like. Right? Each of these lines extends in this way. And so the complete sketch might look something like this. Okay. Typically, when you're asked to sketch some potential solutions, you're not asked for this full thing. You're really just asked for like half of it. Okay, but this is just showing you how you can move back and forth between these things. So this horizontal axis is this vertical axis here. Okay. Let's see how this looks for a couple other things. So one, let's quickly answer the other thing we asked. So say now that y of t sub I is equal to minus 1. Well, that is an initial value here. What's the limit as t goes to infinity of y of t? Well, minus 1 is a stationary solution. Right? And if we believe that we have named these in an apt way, right, so that we've actually done a good job with the terminology here, then stationary solution shouldn't move, right? And it doesn't. So if I'm here at minus 1, there's nowhere else for me to go but along this trajectory that's just a horizontal line here, constant function minus 1. So if I start at minus 1, I stay at minus 1 forever. Okay, also, might as well write it out just for completion's sake. What's the limit as t goes to minus infinity of y? Well, it's also minus 1. From the same picture, if I'm here, I stay here, going in the other direction just as well. Okay. All right, so that indicates how the end behavior is affected by this portrait. Okay, let me draw another couple of pictures here just to show you how this goes. So let's pick some values between 0 and minus 1. So between 0 and minus 1, I'm going to pick something like here. Between 0 and minus 1, the arrows indicate a motion towards 0 as t goes to infinity. So this would look like this. And maybe if I was a initial point here, it would look like this. Okay. What about from minus 1 to infinity? So values here. So the arrows indicate that if I have initial points or initial values, say to the left of minus 1, so less than minus 1, these arrows indicate a motion off to minus infinity. So it would be something like this. Like this. Right? And this. Okay. Between 2 and 3, the arrows indicate a motion towards 3. So maybe this is what a potential solution looks like. Maybe this. So another potential solution in that interval looks like. And above 3, right, for initial values greater than 3, these arrows indicate motion off toward positive infinity. And so maybe this is what I have. Maybe this is what I have. Okay. So this line, this phase line or phase portrait, gives rise to, like, if this is all you have access to, you can reproduce this image that shows you what potential sketches of solutions having various different, so each one of these, right, each one of these points here, including the stationary solutions, indicates a choice of initial condition, a choice of initial data. Okay, and then the trajectories emanating from these points show some potential, what the solutions could look like. Now, these are sketches, right? So the point here is that this is meant to indicate long-term behavior or end behavior, asymptotic behavior. That's really what you're getting at here. For for more fine behavior, this isn't going to cut it, right? So if you want to have point-wise, values spat out to you of what a solution is, you would actually have to solve this thing, right? So this is something that's lower tech, right? We didn't have to solve anything here, but we were still able to figure out quite a bit about what these solutions look like. Okay, so we've answered almost everything that we set out to answer. So identify stationary solutions to this equation, did that. Sketch some potential solutions and indicate their long-term behavior. Yep, well, that's exactly what we just finished. Answer questions about long-term behavior of the form, like if I specify an initial value, what are these limits? We did that. So then the last thing left to do is classify the stability of each stationary solution. So what do we mean by stability? If you're looking at this picture, uh, stability in general in math, not just in this context, but in general in math, when you have questions of stability, this is a question of how sensitive some object is to ideally small perturbations. Okay, and so the idea here is if I look at this or if I look at this picture, if I begin with initial values, say, really close to 0, the question is, do I remain close to 0 as t goes to infinity? Okay. If I do, then we would say that 0 is stable. Okay. If I don't, right, I would say that 0 is unstable or something other than stable. Okay. So let's actually look at 0 here, for instance. If I'm very close to 0 on the left-hand side, do I stay close to 0 as t goes to infinity? The answer is yes. The arrows indicate that, right? If I'm really close to 0 on the other side, do I stay close to 0 as t goes to infinity? Yes. Again, the arrows indicate that. So on either side of 0, right, points near 0 stay near 0. You can see that very easily here in this picture. You can see how 0 kind of groups up these solutions, right? It like bundles them up. These things are getting closer and closer and closer to 0. Okay, so in this case, 0 would be called stable. Okay, 0 would be called stable. All right. Well, what about some of the others? So what about -1? So let's ask the same question. If I'm very close to -1 on either side, do I remain close to -1 as t goes to infinity? When we say close, right, we hopefully mean that as t goes to infinity, this gets arbitrarily close. But in this case, do I remain close to -1? Because you might say, okay, well, as t goes to infinity, you're not at -1 here, you're getting pushed towards 0, but 0 is only 1 away from -1, so maybe that's close to you. We mean arbitrarily close, so this is, this is a fixed distance 1 from -1, so we want it to be closer than that. And on the other side, of course, is not close at all. So here, if I begin near -1, as t goes to infinity, I'm going off to -infinity, so definitely not remaining close to -1. If I'm close to -1 here initially, I get pushed off towards 0. Again, we don't consider that close. You can see in the picture that -1, unlike 0, -1 is pushing things away, right? Whereas 0 is gathering things up, -1 is pushing things away. This is called an unstable point. Okay, so this is unstable. So -1 is unstable, 0 is stable. Okay, so stable if you have arrows going towards it on both sides, unstable if you have arrows going away from it on both sides. So based on that, what is the stability of 2? Well, it's pushing things away on both sides, so it is also unstable. Okay. We have one last thing to consider. Again, you can see that it's unstable from the picture, right? 2 is pushing things away from both sides. What about 3? Well, 3 is if I begin at an initial value that's to the left of 3, but close to it, then I remain close to 3. I'm getting pushed towards 3. Now, on the other side, I'm not. I'm getting pushed away from 3. So 3 is gathering things on one side of it and pushing things away on the other side. So this is the notion of being semi-stable. This isn't as important as being stable or unstable. It's a case that is, when you're asked about stability, usually semi-stable. Sometimes people don't even give it a name. In the notes, it's given the name semi-stable. Anyway, this is the full list of cases that are possible here for these types of problems. So this is what is meant by classifying the stability. So if I go back to my original question list, what did we want to do? Identify stationary solutions. Yep. Sketch any potential solutions that indicate long-term behavior. Yep. Answer questions about long-term behavior of the form asking what the limits of these things are as t goes to infinity. Yes. Classify stability of each stationary solution. Yes. So we've done that too. All right. So that is that. Now, the question is, what other sorts of things can you be asked about these types of problems? Well, nothing really. That's pretty much it. As far as things that can be asked, this is more or less gives you a pretty good example of every sort of thing that you could be asked in this case. So let's do another quick example. This is done in the textbook, so we'll just do this quickly. Right, so I'm not going to rewrite all the things asked. I'm just going to quickly kind of do a phase portrait for this thing. All right, so you might notice that this right-hand side, it's not given to us in its factored form, but I can go ahead and factor it if you like. All right, so I can factor this as this is y times 4 minus y squared. 4 minus y squared factors further, so this is y times 2 plus y times 2 minus y. From this, I can immediately write out the stationary solution. So that's the first step, right, to these problems is always identifying stationary solutions. What are stationary solutions? So again, we get 0. Here we have minus 2, and here we have 2. So if I'm drawing phase portrait line, here's 0, here's minus 2, here's 2. Okay, so 3 points. Breaking this into 4 pieces. Let's check the sign of this quantity on each piece. When I'm to the left of minus 2, so you're thinking of values like minus 3 and smaller, this is negative, negative, negative. So that is, wait, so let's see here. So this is negative, negative, positive. There we go. So so minus, minus, plus. So this is negative times positive. That is positive. All right. So that indicates my arrows are moving to the right. Okay. When I'm between minus 2 and 0, so you're thinking of values like minus 1, this is negative, positive, positive. So negative. And my arrows move to the left. Between 0 and 2, so you're thinking about values like 1. This is positive, positive, negative. Or sorry, positive, positive, positive. So this is positive again. And the arrows indicate motion to the right. And then lastly, positive, positive, negative now. And arrows move to the left. Okay. So, quick question from this. Which of these are stable, which are unstable? Well, minus 2 is stable, right? Both arrows on both sides are moving towards. 0 is unstable. 2 is stable. Okay, for the same reason. If y has initial value, say 1, what is the limit as t goes to infinity? Well, as indicated in this picture, initial value 1 puts you in this spot. The arrows indicate motion towards 2, so this is 2 is that limit. Okay. All right. right, if y of t sub I is equal to minus 50, what is the limit as t goes to infinity of y of t? So minus 50 puts you on this piece. The arrows indicate motion towards minus 2, so this is minus 2. What's the limit as t goes to minus infinity, in this case, of y of t? Well, this is increasing to minus 2, so this is minus infinity. Right. Now, some of these questions are a little bit less commonly asked. This is something, for instance, that's not really asked in the example posed in the notes, but this is the kind of things that you can think about when you're being asked questions about the long-term or end behavior, asymptotic behavior for an autonomous system or an autonomous equation. Okay. All right. If I wanted to sketch, right, a few potential solutions here, my stationary solutions, pretty easy to sketch in. There they are. All right, so here's y equals minus 2, here's y equals 0, here's y equals 2. A solution that has, so again, here, if my initial value is 1, then I am increasing to 2. Right. If my initial value is minus 50, right, and I'm here, I'm increasing to minus 2. Okay. Between 0 and minus 2, say minus 1, arrows indicate motion towards minus 2, so I'm decreasing to minus 2. And above 2, say y is equal to like 10 or something, arrows indicate motion towards 2, so I'm decreasing to 2. Right, something like that. Okay, so that's how these problems work. All right, so once you've seen a couple of these and you've kind of acquainted yourself with, with how this process works, testing the sign and all that, this is, more or less, there's no tricks here, there's nothing unexpected. This is how these problems go. All right. Okay, so that's phase portraits for autonomous equations. This is one example of a crude sort of analysis that gives us actually a lot of info on asymptotic behavior for solutions to this. Notice we did not have to solve an equation at all here, right? There's no solution of any differential equation that occurred whatsoever. This is purely doing some basic algebra and just thinking about what that meant for, oh, I have an unknown function. I know the sign of its derivative, and I can tell by existence and uniqueness, since it can't touch or cross these other existing stationary solutions, this puts a restriction on its end behavior. This tells me exactly what it is doing at its ends. All right, and that's pretty awesome. The only drawback here really is that this can only be done for autonomous equations. So this only works when you have a first order equation of the form dy dt is equal to g of y. So if your equation is not autonomous, if it can't be written in this form, this sort of analysis does not work at all. So you just can't do it. But in this case, this gives us, even though it's crude, right? We're not solving the differential equation. This gives us a nice amount of info. Now, there's another thing that's mentioned in the notes, but typically it is only mentioned in the context of generating it with a computer. And that is the notion of a slope field. Okay, now you could do this by hand, but it's so tedious and kind of pointless. I just wanted to kind of indicate, so direction fields or slope fields. They are another example of a graphical method that can be used to they're kind of crude technology that can be used to glean some info about behavior of the solutions, but it's a lot less info than the phase portraits. But the upside is that it can actually be used for any sort of first order differential equation. So suppose now I have a first order differential equation of the form dy dt is f of ty. Okay, well, this is just some function big F, and even this, if I restrict this to being a continuous function, this is still a very, very general type of problem, right? This is basically everything. So you are, this is not necessarily separable, not necessarily linear. This could be a very, very, very general sort of problem. And so to generate what's called a direction field, the idea is that I should write it out. Idea at each pair, say t sub I, y sub I, f of t sub I, y sub I, being the right hand side of this, tells me the value of dy dt at that point in the ty plane. i.e. it tells me the slope of the tangent line, right? i.e. it tells me the slope of the solution y at each point. Now, to give you an example of how this would work, right? Maybe I have the equation dy dt is equal to like t cubed plus y cubed, right? So this is nonlinear. It's also non-separable. So I have no hope of solving it with the current methods I have. Okay, and so I could, however, plot what the value of this is at different points. So for instance, my big F of ty in this case is t cubed plus y cubed. So I could just, you are going to see very quickly why this is done via computer and not via hand. I could just compute, say f of 0, 0. Well, that's 0 cubed plus 0 cubed. That's easy enough. That's just 0. So then at the point 0, 0, I would draw in a little horizontal line piece that's saying, well, at that point, the slope dy dt is equal to 0. So it's a horizontal line, right, is my tangent line. What about f of like 0 minus 1? Well, that's 0 cubed plus minus 1 cubed, which is minus 1. So that's the point 0 minus 1, which is like here. And at that point, I have a slope of minus 1, which is a negative slope. Looks like that. At f of 0, 1, this is 0 cubed plus 1 cubed, which is 1, so it's a positive slope. So that's 0, 1 here. So this is what my slope looks like. It's positive 1 slope. And of course, this gets more and more positive on this vertical line, t equals 0 here. This is going to get more and more positive as y gets more and more positive because it's y cubed. And it's going to get more and more negative as y gets more and more negative. Okay. And of course, I've just done that for a few points, but you can now imagine generating like a mesh grid of a bunch of points here. So here's like the next line in the grid. So a few points here, and you do the exact same thing, right? So here at 1, 0, right, what f of 1, 0, the value of that is 1, so it looks like that. And at 1, 1, it's 2, so it's a little bit more steep, and so on. Here, it's 0. Here, it starts to be negative again, and so on. And so you can imagine, like I said, generating a grid where you have these slopes, okay, at each of these points. So what this can do, for instance, is, so of course, like, how much info is this telling you? Not a, it's not telling you a huge amount. It can tell you kind of, sort of, the shape of how these things go. So for instance, a potential solution to this could look something like this, maybe, right? Maybe that's like an okay potential solution. All right. And you can see that basically as indicated by this direction field or slope field. So you generate a whole mesh grid with these little tiny indicators of slope. That's your direction field or slope field. So that's how to think about this. Maybe here's another way, right? Here's another solution. Maybe that's okay, right? Indicated by this slope field. This is something to be aware of, just because, like, if you can't do anything else to analyze this, right? Which there's plenty of numerical methods. We're going to talk about at least one of them. Okay, but there are plenty of numerical methods you can talk about to be able to analyze these things numerically. So that's typically what we're going to do if we absolutely can't do anything else. But if you didn't have those numerical methods at your disposal, what can you do? Well, you're in a situation where you definitely don't have an autonomous system, so you can't do phase portraits. So, like, what else can you do? Say you can't solve the thing in question. What else can you do? Well, this is kind of like the bare minimum you can do. It doesn't give you a whole lot of info, but it does tell you, a little bit about what kind of shapes of the solutions you can expect, right? Now, something that I didn't really stress that much, I mentioned it, I think, once, which is that, of course, if we can explicitly solve the function, or the equation, say dy dt is equal to f of ty, then we can just plot the solution y, right? We can just plot y of t. So, this is why, like, explicitly solving a differential equation is the ultimate goal, because if you can do that, then explicitly plotting the behavior of the solution is something you can do, because now you just have a function, right? Y of t. It's just plotting the graph of a function. So you can just look exactly and see what the behavior of this function is just from plotting it directly. Right? You might say, well, what if I can't solve it explicitly, but I can solve it implicitly, right? So an implicit solution can similarly yield an excellent plot. It's just that if it's an implicit solution, it is likely not going to be, some simple function. So for instance, if I had, let's say my implicit relation that solved a differential equation was something like this. All right, what is that? Well, in the ty plane, this is unit circle, right? Now, I didn't really draw that as a good circle, but you'll just have to pretend that that's the case. So there's my curve in that case, right? Right. So this can be handled in MATLAB with contour plot, but and we'll talk about that a little bit more when it's relevant. I will give you the MATLAB info, so you can generate plots like this. So if it's explicit, we're the happiest, but even an implicit solution can yield nice plots of trajectories that these solutions are represented by, or I mean, just it's the trajectories of the solutions. Like if you think about this as some evolutionary system in time, then you can just see the trajectories corresponding to solutions to these equations. Okay. So that's all for graphical methods for now. So now what I want to focus on is what is called in the subsection 6 of chapter 1, applications. So this is 1.6. Right. When the word applications is used in this context, really what it means is tank problems. Not tank as in, the tank that shoots things. Tank is in water tank. So what is the setup? This is kind of the key thing. So rather than go through a full-length derivation of this fact, the main idea is, so typically I'm given a situation involving a tank with some fluid and some described mixture process. Okay, and I'm asked to determine the quantity of something in the tank at some time t. Okay. This quantity I'll call Q. All right, and the idea is we will set this up as a differential equation where dq dt is the rate into the tank minus the rate out. So in the simplest possible tank problem, the idea is that I have some tank. It has some capacity, and it's filled with some mixture of something. Will typically be described as being well mixed. This is just kind of a caveat that makes sure that we have like a uniform distribution of the substance in question. So for instance, if this is some kind of salt mixture, then it's not like we have a medium where the salt is like all sunk to the bottom and is nowhere else. It will be evenly mixed in. So that's where an assumption of being well mixed will come in. So I have a tank. It's filled with some kind of fluid. Into the tank, I think if I have a spout, and into the tank at some rate, I have some other thing pouring in that has some given concentration of the quantity in question. So like I said, salt is a frequent thing that comes up in these problems. So I have some brine mixture in tank, and then I have some other saltwater mixture of some given concentration pouring into the tank, and then rushing out from the tank at some other rate is this well mixed result of this process, right? So stuff comes into the tank, mixes, and then goes out of the tank at some rate. If I want to know the quantity of whatever it is in the tank, right, that's the rate in, so its rate of change here is the rate in minus the rate out. This is kind of the fundamental principle that allows me to set up these differential equations. So with these problems, it really, rather than try to be as general as possible, I think it probably makes the most sense to just do an example to show you how this works. And once you've seen one of these tank problems, you haven't quite seen them all, but it really doesn't take that much adapting to change what it is that's going on here to answer very similar questions. So these are all word problems. So typically it's a giant paragraph of text that you have to interpret. Sometimes you can be given more info than you actually need, which is fine. You just have to be able to identify that. So let's do an example. That's probably the best way to get at what I'm saying here, since, like I said, it's kind of ridiculous to keep these sorts of problems general. So what is the example? This is from the online notes. This is at the bottom of page 3, section 6, chapter 1. Okay, so this example is the first example in this section. So like I said, bottom of page 3. So this is, let me blow it up here so I can actually read this thing. So this says, a tank with capacity of 250 liters initially contains 200 liters of brine, which is a salt solution, with a salt concentration of 5 grams per liter. So a tank with capacity of 250 liters initially contains 200 liters of brine with a salt concentration of 5 grams per liter. Okay. At some instant, brine with a salt concentration of 0.4 grams per liter begins to flow into the tank at a rate of 3 liters per minute. So at some instant, brine with salt concentration (0.4 grams per liter) begins to flow into the tank at a rate of 3 liters per minute. While the well-stirred mixture flows out at the same rate. This well-stirred assumption means that we have some uniform distribution of this thing, and it's not all settling at some point in the tank, so that then we would have to take other things into account. It'd be a more complicated problem. But if it's well mixed, then I don't have to make any of those assumptions. So well stirred. So this well stirred mixture flows out at the same rate. All right, that's important because this is a type of minor thing that can lead to different sorts of problems, right? So, for instance, we can automatically tell that I'm not going to be asked a question about when the tank overflows, because I have a tank with capacity 250 liters, initially contains 200 liters of brine, but if the brine's flowing in at 3 liters per minute and flowing out at the exact same rate, then there's no, the inflow and the outflow are the same rate, so the amount of brine in the tank is always 200 liters, right, at any given point. So actually the fact that this is 250 liter tank doesn't really factor in here at all, but you can see how if it flowed out of the rank, or if it flowed out of the tank at a rate that was less than 3 liters per minute, then eventually this tank will overflow. So questions about when the tank, at the time when the tank overflows, what's the amount of salt in the tank, blah, blah, blah. Questions like that could be asked, okay? But for this example, those sorts of questions can't really be asked because it's flowing in and out at the same rate. Okay, so how long will it take for the salt concentration in the tank to be reduced to 0.7 grams per liter? So how long will it take? So notice, like before I've written down anything, what am I being asked for? How long will it take? I'm being asked for a time. Right, so I'm being asked for a time in minutes, right, for how long it will take for the salt concentration to be reduced to some particular value. So how long will it take for the salt concentration in the tank to be reduced to 0. grams per liter? So there's the actual question, right? Everything else is set up for that. Okay. So it begins at salt concentration of 5 grams per liter. Brine is pouring into it with a salt concentration much less than that, 0.4 grams per liter. The question is, how long does it take for the initial salt concentration to be reduced all the way to 0.7 grams per liter? Now, another rule, I might as well go ahead and mention this since now we have units being brought into this. How much do you have to know about units? Not much. It'll be a little bit more relevant when we get to chapter 2 stuff and you have to remember gravitational constant. Other than that, you don't have to know too much about units. This is not a physics class or anything like that, so I'm not trying to trick you on unit conversions or anything like that, so you don't have to worry about much of that coming from me. So what's the best way of going about solving this? So these problems, the best advice I can give you with all these problems is to draw a picture. Okay, so I draw a picture. So here is my tank. All right, and in my tank, I have brine that takes up some volume. So V of t. So let V of t be volume of brine solution at time t. Let the amount of salt in the tank, in this volume, be S of t. So S of t is amount of salt in tank at time t. Now, it can be helpful to think what units are these measured in. So the volume is measured in liters, right? So volume is measured in liters. The amount of salt is measured, let's use grams, since grams are used everywhere in the problem. So amount of the volume is measured in liters, salt is measured in grams. Okay. All right. So I have volume and salt here, so a couple of things to say. So first of all, the other sort of, so I want to know concentration here. I'm being asked a question about concentration. I have amount and I have volume. What's the concentration? Well, the concentration, so this is the concentration of salt at time t. Well, concentration of salt at time t, that's just amount divided by volume. Right? It's S of t over V. Okay. And so we're getting a more complete picture here. Let's do a couple more things. So first of all, I have inflow and I have outflow. My inflow into tank, what do I know about it? Brine with salt concentration of 0.4 grams per liter begins to flow into the tank at a rate of 3 liters per minute. So 0.4 grams per liter flows into the tank at a rate of 3 liters per minute. The outflow has some mystery concentration that I don't know. It's whatever the concentration is at time t flows out at, and that's measured in grams per liter, and it flows out at the same rate, 3 liters per minute. Okay. So then what is it that I'm being asked when if I look at this box question, what is it that I'm being asked? So I want to find T such that C of T is equal to 0.7 grams per liter. This thing that I've boxed is exactly what this question is. Okay. I have all the info here. No, there's a couple of other things here. One, my tank has capacity 250 liters, but that doesn't show up anywhere here. The initial volume of brine is 200 liters, so actually V of 0, we'll take 0 as our initial time. V of 0 is 200, right? And we also know that the initial concentration was 5 grams per liter, so C of 0 is 5 grams per liter. All right, this is, you can tell what the units are here. It's grams per liter. So while the units themselves and converting between units is not going to be a focus of these problems, one thing that you can use the units for in these problems is to basically cheat a little and let you know whether the thing you've written out is consistent, because the units will have to match up, right? If what you're doing makes sense, the units will match up. So whatever quantity it is you're trying to find, the units should make sense, right? If you have a rate with respect to time, then your units for whatever that rate is should not be grams per liter. That wouldn't make any sense, right? It should be grams per minute. Some grams per unit of time is what would make sense. So even though, like I said, the units are not going to form like a focal point of this, they can be used to just help yourself know whether or not what you're writing is going to make sense, kind of in a basic way. All right, so I have the setup and I have some initial data here. Okay, well, one thing I can see is that, okay, well, first of all, this guiding principle that I want to use to set up a differential equation, this guiding principle is this Q is a quantity that's changing with respect to time. So it's not a concentration, it's a quantity. So in this case, the obvious choice is S, the amount of salt in the tank at time t. So that's going to be the thing that we model a differential equation on using this fact. Okay. So, but I'm being asked for when the concentration is some particular value. So how do these things relate? So first of all, the initial volume is 200, but because the inflow and the outflow are both 3 liters per minute, the volume at any time t is also 200. Right? That volume never changes. So the volume is constant because the inflow and the outflow are the exact same amount. So V of t is 200. So then what this means is that C of t is S over V. That's just S of t over 200. Right? So then S of t, for instance, is equal to 200 times C of t. And so, for instance, if I wanted to know an initial value of the salt in the tank, well, that's easy to compute. S of 0 here is going to be 200 times C of 0. That's 200 times 5, so that's 1,000 grams of salt are in the tank at time t equals 0. Okay. Now we're ready to set up the differential equation. So the differential equation is a differential equation modeling the amount of salt in the tank, ds dt. This is rate in minus rate out. How does this how can I write this from this picture? So inflow provides the rate in, and the outflow provides the rate out. Okay, so the inflow is 0.4 times the rate, which is 3, minus the rate out, which is C of t, which of course I can write as S over 200. All right, so this is S, this is not a 5 here, there. S of t over 200 times the same rate, 3. Okay. So notice at this point we could check ourselves if we're not actually sure that we know what's going on here. This is a rate of salt, right? Rate of change of salt. So if the salt's measured in grams, this should be in grams per minute. Well, the inflow has us writing 0.4 times 3, so it's grams per liter times liter per minute. The liters cancel, and I have grams per minute. Same thing is true here. I have concentration times 3, so grams per liter times liters per minute, so grams per minute. So the units work out at least. This is grams per minute. So this gives us hope that what we're doing is right. So this is 1.2, 3 times 1.4, minus 3 over 200 times S. Well, what kind of differential equation is this? So 3 over 200, I can rewrite that as like 0.015. So 3 over 200 is 0.015. And so I can rewrite this as ds dt plus 0.015 s is equal to 1.2. And of course, I also have this initial condition that I figured out on the previous page. S of 0 is 1,000 grams, so S of 0. Here's my IVP. What kind of equation is this? Notice, this is linear. In fact, it's linear and it's already in normal form. So I can immediately write out the solution here, right? So I can immediately write out the solution. So what is it that I'm looking for here? So I first of all, just following the recipe, I can say, okay, S of t is here is my a of t, here is my f of t, and so big A of t is the integral of little a of t, but little a of t is just a constant, 0.015 dt. So this is 0.015 t. So this is going to be e to the minus 0.015 t times the integral of e to the 0.015 t times 1.2 dt plus c times e to the minus 0.015 t. Okay, so there it is. It's just me following the recipe here. Of course, I have a 1.2 times all this, so this is not anything amazing here. I would have to have a 1 over 0.015 showing up here. So this is e to the minus 0.015 t times 1.2 over 0.015 times e to the 0.015 t. Okay. And so what do I get here? or sorry, plus, I have the second term here, plus c e to the minus 0.015t. These two e's, I get e to the 0 here, so this is 1.2 over 0.015 plus c e to the minus 0.015t. 1.2 divided by 0.015 is, well, actually, we can go ahead and just, this is what my general solution to this is, but I can impose the initial condition s of 0 equals 1,000 here. So 1.2 divided by 0.015, what is that? Let's see here. So that's 80. So this is 80. So this is 80 plus c e to the minus 0.015t. So here's my general solution. I have this initial condition I need to impose, so I'll do that on the next page. So s of 0 is 1,000, but this s of 0 is also 80 plus c times e to the 0. Right? So this is 920 is what c turns out to be. Right? Just subtract 80 from both sides. And so my unique solution to the IVP that I set up is 80 plus 920 times e to the minus 0.015t. Now, this gives me the solution to that differential equation, but let's go all the way back to the beginning. What was I actually asked? How long will it take for the salt concentration in the tank to be reduced to 0.7 grams per liter? Well, that we saw was the same as asking for T such that the concentration was 0.7 grams per liter. But the concentration is S over 200. So I'm looking for big T such that the concentration of big T is equal to 0.7, but the concentration of big T is S of big T over 200. Multiplying 200 times 0.7, this means I'm looking for a big T such that S of T is equal to 140. So I want to solve the equation S of T is equal to 140. But what is this equation? This is the equation 80 plus 920 e to the minus 0.015 big T is equal to 140. Subtract 80 from both sides. I get 920 e to the minus 0.015 big T is equal to 140 minus 80 is 60. Divide both sides by 920. I get e to the minus 0.015 big T is equal to 60 over 920. Take the log of both sides. I get that minus 0.015 big T is equal to the log of 60 over 920. Divide both sides by minus 0.015. And I get that my time, big T, is minus 1 over 0.015 times the log of 60 over 920. It's perfectly reasonable as a final answer. Just to check that it makes sense, this time should be positive, of course. Log of 60 over 920. 60 over 920 is less than 1, so the log of 60 over 920 is definitely negative, so minus minus is positive at least. What is this roughly? This is, I could write this as, let's see if I had to write this out in minutes. This would be, so what is natural log of 60 over 920? It's like minus 2.73 roughly. So this would be like 2.73 divided by 0.015. What is that? 182 minutes, if I did that correctly. So it'd take a little over 3 hours, okay, for this to happen in this way. This is a really good example because it kind of shows you exactly the sort of thing that you could be asked. The more typical variations on this problem are you could be given inflow and outflow rates that are different. So you could be given an inflow rate that is greater than the outflow rate, so the volume is not constant, it's changing. In which case, usually it's changing in a very simple way. So, maybe it's adding like a liter per minute. So in here, this would be 200 plus T. If T is measured in minutes, it's adding a liter per minute. So the volume would be, instead of being 200, it'd be 200 plus T. And you might be asked, rather than it being phrased in this way, you might be asked like, at what time does the tank overflow? Or you might even be straightforwardly asked like, what is the amount of salt in the tank at the time when it overflows? Okay. You could even more straightforwardly just be asked directly, what's the amount of salt in this tank at the time, t equals, like 180 minutes, right? 3 hours. So if you're asked directly for the amount of salt, of course, that's just applying this formula that you found. Anyway, so that is it for applications. I may revisit this. I may do like one quick example on Monday, at the beginning of Monday's lecture. I also might not. I might skip it depending. So have a look at homework 1 if you haven't already. So I just posted it to Elm. So definitely have a look at that. It covers linear and separable equations. You will have another homework that I will post on Monday that covers phase portraits and application problems like this, and that will be due, we'll say, on Wednesday. And then I aim to finish Chapter 1 stuff by the end of class Wednesday so that we can start a little bit of Chapter 2 stuff, and then your first exam, which will be like a glorified homework. It'll just be longer, and you'll only have a day to do it. That will occur the week after. So I'm aiming for, I believe I said I would post it like, when did I say? I think I actually said the 6th. I may post a little bit earlier than that. So I may post your first exam like more like the 13th or 14th. I think that makes sense. Well, I'll think about what I'm going to put on it. It could cover a little bit more. Yeah, maybe I'll do that. So maybe I will stick to posting it like the 16th or 17th, and then it'll just cover a little bit more, because by next week we'll finish Chapter 1. So anyway, yeah, I think that makes sense. Yeah. So I'll stick to the schedule that I mentioned in the syllabus. So anyway, so have a look at that, and I will see you